Okay, so now we're going to do some rational numbers here. Let's start off with the number 1/3. What is 1/3 as a decimal? Well, some of you may know that. That might be a pretty easy thing to just write down. But if you don't, well, any fraction we can do, we can just write 1 divided by 3. There's 1/3 and hit enter. And what is that? Oh, yeah, I did know that. 0.3 repeating. All right, so 0.3 repeating is 1/3 as a decimal. And actually, anything that could be represented as a fraction is considered a rational number. So 1/3 is a rational number. 0.3 repeating is a rational number. Something else, well, of course, anything represented by a fraction, like a fraction, or even a decimal here, like 8/10, which is, or 4/5. That's also can be, because it can be changed into a fraction. Negative ones are the same thing. Or negative decimals, or they don't even have to be 0 point something. It could be 1.5. That's like 1 and 5/10, or negative 1 and 5/10. We could even have a -5, which is like -5/1. There's a fraction. Or 7/1. That's a fraction. All right, so these are all numbers that can be represented by rational numbers. And even, as we just learned in this last one, repeating decimals. In fact, all repeating decimals are also rational numbers. Okay, so that probably starts to get us to think about, well, what is a number that's not can't be represented by a fraction? And the reality is that you guys probably have a friend that have actually memorized one of these to many digits. Now remember, a repeating decimal that goes on forever like that is a rational number. But if it's a decimal that goes on forever that doesn't repeat itself, and again, most of you guys know people who've memorized pi, kind of completely useless activity, but and memorized pi to some significant digits. Some people know it too, because obviously you can't ever memorize the whole thing because it goes on forever. Well, that's an example of an irrational number. A decimal that goes on forever without repeating itself would be an irrational number. Okay, and some other ones that we're about to get into right now, here's some examples. Like the square root of 3. Well, I know the square root of 4 is 2, but the square root of 3 is actually an irrational number. If I plug that into my calculator here, if I do square root of 3, it gives me an approximation, 1.732050808. It looks like it's going to be a repeating pattern, but if this calculator gave me more significant digits, I would be able to see that it goes on and on forever without actually repeating itself. That is an irrational number. Okay, so both rational numbers and irrational numbers make up the category of real numbers. All right, so we need to come up with a number that is not a real number. Uh-oh, wait, something that's not real? You guys may have actually heard of this, and I remember when I was a student, this whole concept just made me so angry. You know, it was hard enough to work with real numbers that my teachers were just going to make things up, and there's something called the imaginary numbers. And I was like, what? Imaginary numbers? Come on, math is hard enough with the real numbers here. We don't have to make things up. And actually, imaginary numbers is probably a bad name for it. It is not something made up. It's actually something useful, and we can actually use it to calculate some things. We use it in astronomy. We use it in electronic circuits. These numbers are actually useful, but it doesn't fall into what we call the real number system. And basically, and you guys have maybe seen this before, if you took the square root of a negative number like this, that is actually imaginary. You've probably learned before that you can't take the square root of a negative number. Well, you can't get a real number, but you can get an imaginary number. In fact, the answer to that is I root 7. And I is actually the imaginary number. And I is actually the square root of -1. It's the simplest imaginary number that there is. So anytime we have a square root of the square root of a negative number, we are going to get an imaginary number. So if you see I or the square root of a negative number, that's when you know you're no longer in the real number system. You are in the imaginary numbers. All right, so now I need to give several numbers that are whole numbers. Whole numbers are basically the counting numbers, plus with the addition of starting with 0. So I have counting numbers 0, 1, 2, 3, 4, etc. Those are the whole numbers. Are all of these rational? Meaning, can they all be turned into a fraction? 0/1, 1/1, 2/1, 3/1? Yes, they can. They are all rational. Okay. Give several numbers that are integers. Okay, integers are basically just, we're taking the set of whole numbers, and the integers include these whole numbers. But we also include the negative ones. So for instance, if I have like -4, -3, -2, -1, 0, 1, 2, 3, 4, etc. These are the set of integers. I'm not talking about any of the fractions in between. Integers do not include the fractional parts that are the pieces parts that are in between these. These are all the integer numbers here. Okay, so which of those ones that I just wrote down are not whole numbers? Well, these are all whole numbers up here, 0, 1, 2, 3, 4. It's all the negative ones in here. So the ones that I wrote, -4, -3, -2, and -1. Which of these are whole numbers? Well, these ones over here that are included in this set, which are 0, 1, 2, 3, 4, etc. there. Okay, so now I need to give three numbers that are rational but are not integers. Okay, again, rational numbers can be represented by a fraction, but they're not integers, which means they're not basically into these whole or integer parts here. So if I do something like 1/2, that's a fraction. That's not into one of the. That's not an integer. All right. I could also write a decimal, like 3/10. That is rational but not an integer. Okay, and so basically, they're the decimals or fractions in between. I could even do 5 1/3. There is a rational number, but it is not an integer. 5 and 6 are integers, but 5 1/3 in between is not. Okay, now give three numbers that are irrational. We had some other examples. But pi is the most obvious one. This is when changing it to a decimal, it's a decimal that goes on forever without repeating. When I take the square root of a number that is not a perfect square, like the square root of 5, or even a negative square root of 13, those are numbers that are irrational. They cannot be represented by a fraction. All right, so can you have a number that is a whole number, but not an integer? So here's my whole numbers. Are any of my whole numbers not integers? Well, integers includes all the whole numbers and the negative ones there, so no, that's not possible. Can we have a number that is an integer, like one of these, but is not a whole number? Absolutely, these negative ones are. So something like -5, there we go, is an integer, but not a whole number. All right, so now we're going to draw a Venn diagram that shows basically real numbers, irrational numbers, rational numbers, integers, whole numbers, and then put these numbers into that set. Okay. I could also have imaginary numbers over on the side, but I'm not going to do that for this particular one. Most of you are used to seeing Venn diagrams as circles. I actually, just to make it a little more organized in here, it doesn't matter what shape I use. I'm going to use a big rectangle to show basically all of my real numbers. They all fall into here. So these are everything inside this rectangle is a real number. Now I'm going to break up that into two different categories. I'm going to put in irrational numbers. All real numbers are either irrational or the opposite, which is rational. Okay? So an irrational, basically, there are no other subsets that we put into them in general. So there are quite a few more subsets of rational numbers, so I left more space here for those. Okay, in the rational numbers, again, these are anything that could be represented by fraction. I also have these integers and these wholes. So I can make this a little bit smaller by I'll put in a rectangle in here that are integers inside here. Okay, and then inside integers is the category of whole numbers. All right, so now what I'd like you to do is put these numbers inside your Venn diagram and then check to see if you got in the same places as I do. Okay, so here are all the numbers plugged into my Venn diagram. A couple of tricky ones in there. Square root of 9, remember that that's a perfect square. So the square root of 9 is 3, which is actually a whole number. 2.00 is 2, so that's also a whole number. And when I simplify 10 over 5, that's also the number 2, which is also a whole number. Just like negative 7.0, because it's 0.0, it's the same thing as negative 7. That makes it an integer, as does negative 12 over 6, which is actually negative 2, which makes it an integer as well. All these square roots that are not perfect squares, they are irrational, so they go over here. But the square roots that are perfect squares go into either wholes or integers when we simplify them. So now we're going to take a look at certain numbers here and try to figure out what sets they belong to, whether they're real, rational, irrational, integer, or whole. So this is a decimal that continues on forever, but it has a repeating pattern. Remember, like 0.3 repeating was 1/3? Well, that's something. Anything that has a repeating decimal can be represented as a fraction. That means it must be a rational number. Now, all of these are going to be real unless we have the square root of a negative number. So we have real. Then we have to choose between rational or irrational, and this is a rational number because it can be a repeating decimal, can be turned into a fraction. It is not an integer, and it is not a whole. This one is the square root of 36. While we have a square root, it is a perfect square, and in fact, square root of 36 is 6, which is a whole number, which means it's basically not only is it real, but it is rational. It can be made into a fraction, but it is also an integer, and it is also a whole. Okay, now this square root here is not a perfect square. It is still real because it's not the square root of a negative number. The negative is outside the square root. If it was inside, it would be imaginary. It would not be real. But it is real, but it's a square root of a not perfect square, so that means it cannot be made into a fraction, which makes it irrational. Okay, so now we're going to start doing some estimations here, all right? I want to try to estimate the square root of 6. Well, off the top of my head, that's not a perfect square, so that actually is kind of difficult. But if I do this, if I know that a square root that I do know, for instance, that's below it, let's say the square root of 4, all right, I know that that's 2. Now the square root of 6 is what I don't know. Now, if I have a number that's below it, how about the next perfect square that's above it? The square root of 4 is 2. The next one's going to be 3, which is the square root of 9. All right? And so if the square root of 6 must be somewhere between 2 and 3. It's going to be 2 point something. All right? Because the square root of 4 is 2, square root of 9 is 3. Square root of 6, which is in between 4 and 9, has got to be between these two. So it's got to be in between the numbers 2 and 3. Now, what I like to do is take a little note here and notice that the 6 is actually 2 units away from the 4, and it's 3 units away from the 9. So it's actually closer to the 4 than it is to the 9, which means it's going to be closer to the 2 than it is to the 3. So 2.5 would be right in the middle, but like we just said, it's actually a little bit closer to the 4, so it's got to be a little bit closer to the 2. So 2.5, something a little bit closer to the 2, maybe something like 2.4 or 2.3. All right, so I throw that in. Now, I'm just going to check to see how close I was, and then we'll have a little quick discussion about that. I want to do the square root of 6 here, so I do square root of 6, and I get 2.44, okay? All right, so to the nearest tenth, I got it. Now, if you're off by 1/10 on there, I'm not going to take any points off. So in other words, if you had guessed 2.3 or 2.5, then I wouldn't have taken any points off for that. But if you'd gotten a little bit too close, 2.2 or 2.6, then I would have taken some points off. We should be able to get fairly close just by using this estimate practice here. So the closest we get is 2.4. That's our approximate. Now, let's try negative the square root of 3. Well, I'm going to ignore the negative for a minute here, and I'm just going to take care of the square root of 3. So if I'm going to do the work over here. All right, I'm going to find the two perfect squares on either side of the 3, which are 4 and 1. Square root of 1 is 1, square root of 4 is 2. So square root of 3 is going to have to be between 1 and 2. In other words, it's going to be 1 point something. All right, which one is it closer to? Well, let's see, it's 2 units away from 1. It's only 1 unit away from the 4. So it's going to be closer to the square root of 4, or in other words, closer to the 2. All right? So, and then this is actually kind of challenging. We have a 2-to-1 ratio here. I'm going to say we're somewhere around 1.7 is going to get that. And the reason why is because it's about twice as close to the 4 as it is the 1, which means it's going to be about 2/3 of the way up, which is around 0.6 repeating, but it doesn't, square roots don't work exactly that way, so again, I'm just approximating. All right, let's test my theory here. Square root of 3, oh, actually, I already did it on my calculator here earlier. There I got 1.73, so 1.7 is pretty good. Now, I have to remember that's negative, okay? So on a number line, if I put in some, let's say -3, -2, -1, 0, 1, 2, 3, 4, etc., okay? Square root of 6 is around 2.4. 2.5 is right here. 2.4 is basically a little bit less than that. So the square root of 6 is approximately right there. And negative square root of 3, that was negative 1.7. All right, so I should have that's negative 1.7. So here's 0, -1, -2. Negative 1.5 is right here, a little bit closer to the 2. Right here is negative 1.7, which is approximately where negative square root of 3 is. Okay, so now I've been able to place those on a number line. All right, the next part here can be a little bit challenging. So this next part here may look like it's fairly easy in terms of just putting an inequality symbol in here, which one's greater than or smaller. But actually figuring out which one's greater or smaller or equal is actually quite challenging here, unless you know a really good strategy to be able to do it. So I want to start off with just pretending I don't know any strategies and seeing if I can figure this out. All right, the square root of 7, and again, this is assuming I don't have a calculator, because if I had a calculator, I could compare these a lot easier. But this we are assuming we don't have a calculator. So I'm trying to find the square root of 7 here. Now, back here I did the work for the square root of 6 up here. Well, square root of 7 is a little bit closer to 9, so I'm guessing it's going to be around 2.6, 2.7, somewhere around there. So I think it's going to be somewhere around 2.6, 2.7 now. But again, I'm just approximating. Now, 2 2/3 is actually 2.6 repeating. And that's a little bit challenging here because this is greater than that one but smaller than that one. So you can tell they're really close. So this method of just kind of approximating is not going to work. All right, so here's what I'm going to need to do. I'm going to need to square both sides. And the reason why I'm doing that is because the opposite of a square root is a square. That makes this one really easy. Square root of 7 squared is simply 7. And that's the whole point of making this. We're trying to get rid of that irrational number, making it rational. Now, this one here, this is one, actually I've just made this one a little bit more challenging because I'm squaring a fraction. Well, first of all, I need to change it into an improper fraction. 3 times 2 is 6, plus 2 is 8 over 3. And I'm squaring it, which means I'm multiplying it by itself. So 8/3 times 8/3, okay, which is 64 over 9. All right, and then I actually do need to remember how to do long division. I need to do 64 divided by 9, not 9 divided by 64. A lot of my students always put the big one on, or sometimes put the 64 and the 9 in the wrong spot. But this is 64 divided by 9. The 64 goes on the inside. The 9 goes on the outside. All right, I'm going to put my decimal in here. Okay, 9 goes into 64 how many times? Well, that would be, it doesn't go into 6, but it goes in 64 7 times. 7 times 9 is 63. Subtract, and I get 1. Bring down the 0. 9 goes into 10 once. And I get 9. Subtract 1. Okay. At this point, I can actually stop here because I know that this one's 7 and this one is already 7.1 something, so this one is bigger. Pretty close, but I don't even have to finish this off because I already know that 7.1, whatever else I get here, is going to be larger than 7. So if I know that, then I certainly know that the one on the right is going to be greater. Okay, let's go ahead and try the second one here. I've got 1.5 repeating, and I've got 2.25, square root of 2.25. Now, this one is actually fairly easy if I can recognize that 225 is a perfect square. If 225 is a perfect square, in fact, the square root of 225 is 15, then the square root of 2.25 is actually 1.5. So this one, just by knowing that that this is a perfect square, and I know that this is 1.5, now I'm just comparing 1.5 repeating to 1.5. Well, which one's bigger? 1.5 repeating. Okay. Square root 11, 3 1/3. Again, squaring both sides is probably the easiest way to do this one. unless they happen to be approximating, you were easily able to tell the difference between those, but let's assume it's not. So I'm going to square both sides. This becomes 11. 3 1/3, that's 9 10/3 times 10/3, which gives us 100/9. So now I'm going to do the work over here. 100 divided by 9. 9 goes into 10. Let's see, 9 goes into 10 once. Subtract, bring down the 10. 9 goes into 10 once. All right, so it looks like I have a repeating pattern here. I'm going to get 11.1 repeating. All right, so this one's 11. This one's 11.1 repeating. Which one's bigger? This one on the right. Okay. All right. Decimal is going to be, we're going to do the same thing, except now we're going to have to square a decimal, which is probably maybe a little bit more work in terms of multiplying decimals here. But again, I'm going to square both sides and compare them. Actually, this particular one, I'm going to show you how to do that way. But this one, I know that 4 squared is 16. And it's 4.03 is so close to that I know that the square root of 17 is going to be bigger than that. So I'm pretty safe to do that. But I'm pretty good with numbers to be able to figure that out. Again, you may not be able to see that right away. If you are, that's great. But in this particular case, we can use the same method we've been doing is squaring both sides. That becomes 17. Now we have to square 4.03 times 4.03. I get 16.2409. 16.2409, and obviously 17 is bigger than that. Okay. Last one here, again, if I recognize this as a perfect square, that 625, that one's actually kind of a difficult one to realize there, but that's actually 25 times 25. So this one is square root of 6.25 is actually 2.5, and this is 2.5, which is also 2.5. So these two are equal. So let's see if we can go ahead and apply these square roots into a problem here. On a clear day, the number of miles a person can see to the horizon is about 1.23 times the square root of his or her distance from the ground in feet. Suppose you're 169 feet above the ground. How far can you see? Okay, so if I just look at the first sentence, I need to come up with an equation for this. All right, the number of miles I will call m, and that the number of miles is, there's an equals, about 1.23 times, so 1.23 times the square root of his or her distance from the ground. We'll call it the square root of d. Okay, in this particular case, we're told that that distance is 169 feet above the ground. So I'm going to plug that in for d, the square root of 169. So I get m equals to 1.23 times the square root of 169. 169 is actually 13. So I now have m equals to 1.23 times 13. I did the math down here, and I got 15.99. So that means approximately 16 miles is the answer. I'm going to write about 16 miles is as far as I can see in the horizon. Okay, once you're done with number 15, ask the teacher to give you the squares so that you can make some right triangles and get the directions from your teacher on that.